Here. Okay, thank you very much for the nice introduction. Okay, so I'll present a few recent works on vision-guided robotics. So just to start with, I mean, we've seen this in several of the talks this morning. What we want to do is give instructions to the robot follows the instructions, so it has to understand the language, model the visual environment is very important. I think 3D information is getting back because it's really important, and then it has to plan and execute the tasks. So there's also important that the planning and execution is well done. So I'll present 3 or 4, depending on the time, for our recent works. The first one is LLM-guided 3D policy for robotics manipulation. So here there's an approach where we have an LLM for task planning, then a VLM for object localization, and then a 3D point cloud based for trajectory planning. And one thing, so I'll start with this, is actually that robotics needs better benchmarks. So while in vision we have a lot of benchmarks, in robotics there's not a lot of benchmarks, and everybody compares on their own data, so it's really hard to actually evaluate and compare. And so here we introduced one benchmark, which is GEMBench. And so here the idea is to actually measure generalization across different tasks. So we have a set of training tasks, which you can see here on the top, which are relatively simple tasks. And then we want to see level 1 generalization is how does this generalize to novel object placements. Then just by moving around things, then how can we still understand things if the objects change, like that it's objects which we haven't seen before. Then can it be extended to novel structured objects, and then actually for how does it generalize to long horizon tasks. And I think this is very interesting because obviously if you have never seen these objects before, it won't generalize, so we really need to leverage the LLMs and the world knowledge to actually do this generalization. And so here in more detail, the training set, we have these different action primitives. Then level 1 test set is my level 1 test set is that you have novel placements and distractors. And then basically the next thing is that you have new colors, new shapes. And then here this is more complicated. So for example, you have close the door, and then it's close the door or close the bridge, so that makes it much harder. And then also interestingly is this long horizon tasks where you don't have just simple actions, but you have to chain together actions. And I think this is something which in many cases people don't really examine, because when you really want to execute your robot task, you don't want to have just fold the clothes, but you want to really have a set of actions which you chain together. And it's not just one task, but you really have to see how these things chain together. And then obviously here it's quite simple tasks, but even there it's not completely solved yet. And then if you compare the benchmark to existing ones, you can see ours is more exhaustive and complete. I think one of the things which is maybe also not perfect here is the realism of the vision. So I'll get back to this. Basically, it's like this artificial environment, and this is something which is also important, that it's realistic, right? Because if you want to learn, if you want to transfer knowledge from the real world to the benchmark, it has to be the same visual appearance. And then now we have this benchmark, and then what is our approach here? It's this Lotus C++ approach. So what we do is we decompose the task with an LLM into action primitives. Then we ground the objects with an VLM, and then we have a policy which does this 3D understanding to guide the object. So here just a few of the existing policies, what they take in as input. They take as input point cloud, and then basically text instruction, short text instruction, and then execute the robot action. So it can be either diffusion models, so there's a lot of diffusion models. We have developed these models which take as input 3D point clouds. They're maybe a bit more lightweight because they don't have all these diffusion policies behind them. They can be trained faster. It's probably an open debate still. And then to get the point clouds here, it's pretty simple. We just have the different camera viewpoints with the depth map associated. And this gives us the initial point cloud. It's very simple, it's very quick. And then it goes into this 3D vision transformer. So you have as input the PointNet transformer, PointNet v3. As an encoder, we give in via cross attention the word sequence, and then you get out a set of heat maps which give you actually the position where the robot needs to go. And you can see that basically if you formulate it as a classification task, you get a slight improvement. And then if you look here, comparison to the state of the art, our method at the time was published a few months ago, outperformed the state of the art and was much faster, right? So if you have these diffusion policies, it's very slow to train. And then if you look here at this extension of this, our GEMBench of GEMBench. So this was like on the small 18 tasks of GEMBench, and this is now on our extension here. And you can actually see that if you look at this level 4, where you need to plan several tasks, it doesn't work anymore at all, right? Because there basically you give as input, you can take as input a short sequence, but if you have several steps which you have to execute, it doesn't understand it at all anymore. I think this is probably true for quite a few models, that they can execute simple actions, but if you have to plan, it's not longer possible. They have not been trained for this kind of execution. And so what we do then, we have first an LLM which does this task planning, which gives a certain number of sub-steps. So for example, here it would be grasp, rotate the object, push forward. Then we ground the objects. So we localize the objects in the multiple views in 2D, and then we can have our 3D policy. We take this as input to our policy, and then can execute each of these sub-steps, right? And so here it's like separate components. Obviously, you could also imagine putting them together, but basically by the fact that you separate them, it's more interpretable. But you have now a new approach where you can just integrate everything in one element, and the planning and segmentation is done jointly. Okay, I think I've shown this, and then basically if you do this, you can see that the performance improves. So you can see here, you go from 3% to 17%, but you can see, you can say this is still quite low, and so why is it low? So things which don't work, still don't work so well here, is the object grounding, and the planning is also not perfect, right? So you can see if you have a perfect plan and a perfect grounding, the results are much better. And then basically if you have the object grounding, the performance drops. And this is kind of because the objects haven't been seen before, and so this is kind of going into the direction that we need more data for training, right? So basically here we just trained on this small subset, and it's very clear this is not enough. So then we have an extension where we add more training data, and then obviously the performance improves. So it's really important that at some point you cannot generalize without having seen the things at all, right? So generalization is only possible in these LLMs because they have seen these large amounts of data. So I think generalization, I mean, somebody asked me this question, generalization is actually a term which is not really true, because it's just building on what you have seen, and it's just leveraging all this world knowledge. And then some examples here, you can see that we can generate two new shapes. Like here, for example, close the fridge of close the door of the fridge. We have seen only during training, close the door. So this works. And then we can also generalize to this long horizon tasks where we can stack different colored objects and so forth. And then failure cases. So one here is basically, it confuses the objects. This is something quite often in this quite simple scenario, but I think it's pretty common that if you have too many objects, it kind of confuses the object. And then the other thing is actually, okay, here on the left, that it kind of has problems executing the commands precisely. I think this is one of the problems. I mean, Mark showed this nice robotics hand in his talk, and I think this is actually going away from these problems with all these very clumsy robots. I think there's also a lot of problems still at the hardware side, right? That if you have this gripper, I mean, it just cannot turn correctly to open this fridge door. And so I think there's still quite a lot of work to be done to make the robots, especially for manipulation, better. And then some real-world experiments. Here we can see on the left our 7 tasks for training, which we use for training, and then 5 unseen variations where we change the objects. So this is objects which we haven't seen during training, and we can see here that our approach outperforms existing approaches. If you look at the examples, we can see that it actually nicely opens the door, puts in the objects. Here, an additional example. Manages to hang the pink mug and then the other one, so it's also working well. And then now if you go to these unseen tasks, so this is like the previous approach, no, this is just losing the basic block. So here we can really see if we have these unseen tasks, we really need to decompose our instructions into sub-steps and really execute them sequentially. And then you can see here, it works well. It can stack different types of colors, of cups in different colors, can build up, can pick up different foods, place them in the bin and really recognize them, and you can just add new objects and it learns them on the fly. And then here, now the next example, let's just go to the failure cases. So here, 2 failure cases. The first one is imprecision in grasping, so it doesn't manage to grasp the object correctly. And then the second one is confusion of similar shapes, right? And I think so grasping, and that's why you need more 3D information. Grasping is often still quite difficult because if the 3D information is not precise enough, it doesn't work well. Okay, and then the second part is a critique for robotics. So here, basically, one thing is if you don't grasp the object, it's like there's no real mechanism to recognize that it has failed, and it's not possible to give feedback. And so here, what we claim is that failure detection is necessary to replan. And this actually goes in line with many of these recent critic approaches. So this is not just something which is specific to robotics, but it's also something which is nowadays used for all these large language models. You want to have a critic to kind of see if it works or if it doesn't work. Otherwise, you have no way, it's a black box, and you have no way of really saying if it works or not. And so some of the critics in the literature, they're just building up on the same model. This only works if you have very large-scale models, I think, or at least for now, it only works if you have large-scale models. And so what we do here, we have a critic, which is a VLM, to detect these planning and execution errors. And so here the idea is you have these two types of errors, which is the planning failure. So basically the task, the position can be wrong. So for example, here, if you look at this plan, pick up a pear, put the pear in the drawer, and then what is missing is the task open the door. So we can really see that our model, I explain in detail obviously later, is able to detect this failure. And the same thing, execution failures. Basically, if you have some execution failure, you can detect here that the thing is not executed correctly, and then you say wrong object, state, or placement here, for example. And then you can actually you can actually then go and execute the task again. And so here, how we do this, we have, in addition to having just a yes and no answer, we have also give back the category, so which gives then some indication to the model how to improve it. And then for, obviously, what we also do, we have this thinking mode, which is kind of now standard, that basically you say, you can see here what it's thinking, it looks at the different tasks, then analyzes them, then gives back the answer and the missing category. So this in theory, you could even use this plan to see what's going on, the thinking trace to see what's going on. Similar for the execution verification, so you have the start and end image, it interprets these two images, and then kind of gives back the analysis, right? And so our model, we trained it also to do this thinking correctly. And so what we do here, we have a intern VLN3B model with LoRa adapters. It's quite a small model. We give as input the start and end images, given that these actions are quite short. There's no need to give the intermediate images. We have a text prompt, which tells us what we want to verify, and then an output label, true or false, and then the category of what went wrong. So for example, wrong object manipulated. And then in order to train this model, what do we need? We need to have training data, so we collect training data here. We start with successful plans and generate wrong ones. So here we can see what we take. We take examples from GEMBench, and then the Bridge V2 data set, which is a real robotics data set where people have put up these real robotics data sets. Similar, there's probably not enough, what Mark said before, there's probably not enough of these real robot data sets around. And then for the planning, we have different ways of perturbing the plan, missing subtask, contradictory subtask, wrong order, wrong objects, and so forth. So what we do, we generate this data synthetically, having correct data, and then generate the incorrect ones, the failure cases. And then for the plan execution, so we have two ways of doing this. For GEMBench, we can do online perturbations. So we have the correct action, we can perturb it to make mistakes. So for example, not grab the object. And then for Bridge V2 data set, what we do is we change the text. We also tried changing the images, but then it was too noisy. So what we just do is we say whatever it picked up the spoon, instead of it picked up whatever the towel or something like this. And this gives us the failure cases. Then we had some analysis on the small held out set on real failures. We can show that actually our failure categories correspond well to the real failure cases, so it's not just artificial. And then if we look at the training set, so what we have here, we have the error of fail with training, validation, and test. Then the bridge v2 fail. And then we have also recorded ourselves a small Euro5 fail data set where we have also training, validation, and test set. And then in comparison, what's available in the literature is this RoboFail data set, which is really very small and for which you don't have any training data. And even it's so small that we found that there's like huge variations. I mean, it's just not statistically meaningful. And then if you look at the training, so we just evaluate, this is just using the model by itself. So basically it's chance level, so not great. And then if you train it on our bench here, it would be training on our bench obviously improves. It improves also on the other data sets, and you can see here, if we use these two data sets which we generated, we can see that the performance is it's good. It's also working on RoboFail, which we haven't trained on. It's also working on Euro 5 if you haven't trained on it, and then if you train on Euro 5, you can see that the performance on Euro 5 further improves. And then here, as to be expected, but it's nice to show that basically if you increase the training set, the size of the training data set, the accuracy improves. And then here, the results, a comparison to number of models, large models, then some state-of-the-art results, AHA and Cosmo Reasoning, and you can actually see our model outperforms all of them. And here, this is like our base model, and then this is the improvement, right? You can really see it outperforms the performance. It's already at 90%, for example, here on Euro 5 fail, it's at 90%, so it's actually quite accurate. And then obviously what do we do with this method? What we want to do is we want to insert it in our execution pipeline, so we integrate it in Lotus 3D++. So what we do is here first we verify the plan. Then if it's correct, we go on. Otherwise, we go back and refine the plan. So we have 3 chances, so it tries 3 times. And then for execution, the same thing. You can see here actually it has the sequence. It sees that it didn't hit the right button. Then it says incorrect, retry, and then it manages to do it successfully. And if you look at real-world experiments, so here we have some experiments on our Euro 5 robot with 6 degrees of freedom and 3 relevance centers. And you can see that if we execute the actions in the normal scenario, the performance improves. And then what's perturbation is that somebody just pushes the objects away. And then you can see that the increase is much further because then basically it always fails. So you'll see that somebody is like, well, during execution pushing away the objects, and then basically it fails, right? Because the object was pushed with a button. Okay, and so here, this is the instruction. Put the black grapes back into the cyan plate, then the bananas into the pink plate. You can see here the generated plan. Then here, guarding thinking. It says it's correct. Then the different subtasks are executed. You can see here the raisings are not picked up correctly, so it says try again. The second time it works. Okay. It says true, it's managed to pick them up, and so forth. Next step, move grasp object in the cyan plate. Again, it executes the subtask verification. Here it says true. You can see here that you have actually this thinking trace where you say what's in the start image, what's in the end image, and then you say it's true, and then if it's true, obviously you don't need the category label, but if it's incorrect, it also gives you the category label, which helps you further to improve the execution. And then here another example, stack the pink cup into the cyan cup. And then here it didn't work, so you saw here somebody pushed the cup away, and then you retry it, and then it actually does work. And then the last thing is a failure case. So here, despite the fact that it was able to correctly detect that the banana wasn't picked up, during a retry, it doesn't manage to do it again. And I think this is something where you probably would need to retrain the model better. So for now, we didn't retrain the model with this failure detection end to end. So there, you would probably need to say that what happened, and then kind of have failure examples also in the full Lotus 3 D++ training thing to kind of integrate this better. Anyway. Okay, so then the next part is on learning from human demonstrations. We also saw this a bit in Mark's talk. So what you would want to do is obviously leverage all the video data which is around to learn from human demonstrations. And I think there are a couple of works nowadays around for humans, which kind of mimic human motion quite well. But then if you interact with objects, it gets much harder. And I think so there are a number of problems. Obviously, it's that, okay, here's not the problems, that you need to reconstruct the objects perfectly, and then you need to retarget and take into account the physical constraints. And then obviously, why is this interesting to do this? Basically, RL, if you want to learn from RL, we know it's computationally expensive and it won't work in a general setting. So if you want to learn everything from RL, people have shown that it doesn't really work well. It's very expensive. You have to handcraft all the rewards. Then the other thing is like all these teleoperations. People now, they use teleoperations to manipulate all these robot arms and have collected a lot of data. And then here, what we say is basically the end goal would be to learn from these human videos. You could learn the planning and then also the interactions, right? And so for now, it's still quite difficult to extract this information from the videos. And then here, what is our approach here? We have the human videos, we have the 3D reconstruction, and then we can do the retargeting from the reconstructed hand object to the, okay, why is it not shown? To the retarget trajectory of the hand object interactions. And then what's the problems here is that the reconstruction is not perfect, even if it's nowadays very good, it's not perfect, and then often the interactions of the retargeted robot hand, they're physically implausible. So what we do here is we add a number of, we have this retargeting, and then we add some lightweight RL on top of it to make the picking up actions physically plausible. We do this in state space, and then we map the whole thing into, we roll out the trajectories and then map it into vision-based policies. And then what is important here is to pick the right reward. So we have two types of rewards. One type is where we kind of go to the object, where we just have the localization reward here. And then for the manipulation, we have a number of rewards, which is the hand motion, the object motion, where we take into account the position and the angle, then the number of fingers which are in contact with objects, and the bonus when the object is lifted. And then for the vision-based policy, we have we represent the hand with a pound cloud, but then add a number of reference frames to make it more robust. And then the experimental setting is from previous work where we take relocation, pouring in place inside, and then the XYCB videos, which are quite easy for reconstruction. We can see here that using these two types of rewards improves the performance significantly. So here for this scenario, success rate is at 1% at 100%, so it's perfect. And then if we go to the real world experiments, we can see here, so what we get here for our experiments, we have 80% success rate for seen objects and 68 for unseen objects. And then if you look at it, it works quite well, so we can pick up these different objects correctly. And we can see that it really mimics the hand motion well. But of course, it's still quite simple action, so you just like turn things, you pour things, but it's not super hard. And what's nice here actually is that it can grasp this bottle in quite different poses, so it's also not far from trivial. If the object is like turned and lying like this, to grasp it correctly, it's quite hard. Okay, and so basically we've seen that we can learn from these demonstrations, but I think one thing is still missing is that we still need to have a better understanding of the real world videos. So basically, if you take today a bunch of videos and you tell your robot, learn from these videos to grasp the objects, it's still not possible. And so basically, I'm going to present some of our recent work on grounded video captioning. So this can be obviously used for other tasks than just robotics, but basically, it's kind of useful to not only see what's happening in the video, but also to localize the objects. And once you have localized them, you could potentially also reconstruct them in 3D, or at least you could have it to make a plan or localize. If you use glasses, you could use this to localize things in the image, and maybe you don't even need to go to 3D necessarily. And so what we have introduced there is first a large-scale pre-training data set, then a spatial temporal counted captioning method, and then we have introduced a small iGround data set for training and testing. And so why this large-scale pre-training? Basically, there's the models, the current models are not really trained for this task. And so I think this is generally true. If they're not trained for the task, you need to have this large-scale pre-training data set to really train for this task. And so there is some work around for localizing objects in images. So here there are two approaches which we compared, GLAM and AllWidV2 or AllWidVid, which both actually localize objects and caption them, but that's only for a frame. And so if you want to go and extend this to videos, what we did here is we extracted the subject-verb triplets and then used an LLM to combine these triplets to have one video-level captioning where we have the objects localized in each frame. And this then gives us the localized objects, and to really make sure that the objects correspond to each other, we can either use a tracking approach or an LLM-based approach to match the objects across the video. And so what we don't have yet, but what we could have, we could also have the states, right? So basically here we could really have a very precise description of the videos, and one thing which is also nice with this kind of data, that you make the models more interpretable. So you can really see what corresponds to in the caption to the objects, and you could use this potentially for verification or also for reasoning. And then this is our large how to ground 1 million data set, which we have annotated manually, automatically. So we have this 1 million video clips from how to 1 million, which have timestamps from how to caption, so this is some prior work. Then we have downsampled the videos to 5 frames per second, and then we have automatically annotated them. And if you look at the comparison to other data sets, it's much larger, but obviously it's noisy, and so for evaluation, it's better to have a manual data set, so we've annotated a small data set of 2K videos manually. And then, yeah, here this is the manual annotated data set. I won't go into details. And then here, the approach, it's a standard LLM where you have the video prompts as input, the LLM gives back the caption and the queries, and then you can use the queries to find the corresponding bounding boxes in the video. And then if you look at the results, you can see here that basically this would be automatic annotation. Then here, if you have our method with pre-training, so this is just the automatic annotation. Then if you train a model, you can see that it smooths out some of the noise. Then here the approach with fine-tuning, our small data set, and you can see that basically if you just fine-tune, it's not enough. So you really need this pre-training to improve the performance. And then here you can see that the impact of the pre-training data set, so if you have more pre-training, the results improve. So this would be just the performance with pre-training only, so it improves, but then if you have fine-tuning, it improves in a similar way. And then comparison to the state of the art. So there is the ViViDex data set, which was initially made for referring captions, so it's not very densely annotated. We can see that our approach outperforms state of the art, and in particular, it outperforms concurrent work, which is VideoGlam, by a margin. And then similarly here, another data set, which is the ActivityNet entities data set, where we also outperform the state of the art significantly. And then if you look at the results, you can see that basically it really does localize the objects well, and the hands also. So basically hands is, we don't have a specific hand detector. I mean, if you go for egocentric videos, you could probably add a specific hand detector, but you don't have this here. So it's really completely automatic. So it really finds the caption and the corresponding objects. So here, person is cutting meat into pieces using a knife. And then, yeah, and I think so the thing which is actually nice here is you could use it for robotics, but also it makes your models much more interpretable. So you really know where the objects are, and you could actually then maybe have another method to verify that the objects are there and go one steps further by reasoning about the objects. So once you have the objects, you can really also then use them to reason and have some additional thing where you can really describe what's happening in the video. So this is, I think this is just the start. You can go much further by reasoning about the interactions now, and what's missing is obviously data, right? For now, I mean, this is like, when we did this work, there was no data set to evaluate it, and if you have no evaluation data set, it's really hard to do something. And if you have the state changes, but you could really imagine to extend this to state changes and go much further, and then it could be very useful for robotics. Okay, so basically what we have seen, vision language transformers show good results for action prediction and planning. We've seen that a critic with VLMs is successful, so I think this critic idea is actually something which I quite like right now, because it works in many domains really well. You can really improve the performance significantly, and given that the LLMs, you can actually feed in additional information and then they're actually able to correct their output. It's actually working quite well. And then learning from real-world videos remains difficult. So in addition to manipulations, we can also learn planning sequences, but this is something which is completely underexplored, in particular the planning sequences. I think people haven't really looked at it at all. You could really use these videos to have these planning sequences learned from large amounts of video. And then this is something which Andrea mentioned, but I think this is still something which is quite an open question, how to use this 3D, more precise 3D representations in VLMs. So if you just feed in point clouds or 3D information into VLM, it doesn't work at all, right? And so maybe you could have it in some way coming out of a vision transformer, but for now, I find it still quite hard with this ongoing research. Probably it will be solved pretty quickly, maybe by Andreas or something like this. But, and then you could also include object localization in maps in this blending thing. And I think if the precision is not there, this is something I found all the time. If the precision is not there, it just fails, right? Because if you want to grasp something or manipulate something, you have to have really a very precise representation. And then in the long term, I think what is interesting is to improve these models by real-world interactions. And to do this, we need more robust robots, and it's actually much harder than you would think, right? Because by the time you start having a robot running around the world, it just fails after it crashes. Mark was saying this in the break, it crashes after 5 minutes, and then it goes into repair. So this is something also, I think, on the robotics side, if the hardware was better, you could also do more. And I think we're getting there, for example, with these dogs. They can really plan and learn because they're like much more robust, and you can have them run around. Okay, thank you for extension.